Hello, welcome to my channel. Before proceeding to study, please subscribe to my channel. Today, we will explore the fascinating world of game theory with engineering applications. We'll dive into key concepts like introduction to systems, elements of a system, framing systems, open and closed systems. Let's get started. Slide 1. Introduction to systems. A system is a collection of interconnected components that work together to achieve a specific goal. It can be as simple as a thermostat regulating temperature or as complex as a communication network. Key characteristics of systems. 1. Interconnected elements. Systems consist of multiple parts that interact with each other. Without these relationships, individual components cannot function as a system. 2. Boundary. Every system has limits that define what is inside and what is outside. These boundaries separate the system from its environment. 3. Input. Systems receive input in the form of energy, information, or materials from their environment. 4. Process. Within the system, these inputs are processed or transformed to achieve specific functions. 5. Output. After processing, systems generate outputs that interact with the environment. 6. Feedback. Many systems rely on feedback loops where outputs influence future inputs, ensuring stability and improvement. 7. Goal-oriented. Systems are designed to perform specific functions or achieve particular outcomes. Example: in a computer system, the input is user data, the process involves computation, and the output is displayed results. Significance. Understanding systems helps engineers design better processes, optimize performance, and troubleshoot complex problems. Slide 2. Elements of a system. Every system, regardless of its complexity, consists of core elements that define how it functions. Essential elements of a system. 1. Input. Raw data, energy, or signals received by the system from the external environment. 2. Process. The internal mechanism where inputs are transformed into outputs. 3. Output. The final product, service, or result delivered to the environment. 4. Control. Mechanisms that regulate the system, ensuring it operates within desired parameters. 5. Feedback. Information returned to the system to guide future operations or adjustments. 6. Environment. External factors interacting with the system that may affect its performance. 7. Boundary. Defines the limits of the system and separates it from the surrounding environment. Example: in an ATM, input is the user's request, the process is transaction verification, and the output is cash or a receipt. Significance. Identifying system elements is crucial for analyzing, designing, and maintaining efficient systems across various engineering fields. Slide 3. Framing systems. Framing a system means defining its scope, purpose, and interactions clearly. This process helps in understanding how the system operates and interacts with external factors. Key aspects of framing systems. 1. System scope. Identifying the system's boundaries and limits, specifying what is included and excluded. 2. Purpose. Clarifying the system's goal or function, which drives its design and operation. 3. Stakeholders. Recognizing the people or entities interacting with and affected by the system. 4. Components. Listing all parts of the system in their relationships. 5. Processes. Defining the sequence of actions that transform inputs into outputs. 6. Interfaces. Describing how the system interacts with other systems or users. 7. Constraints. Recognizing limitations like time, resources, or regulations. Example: framing a traffic control system involves defining vehicle flow, managing signals, and optimizing traffic patterns. Significance. Framing systems ensures clear design, efficient functionality, and easier maintenance in complex engineering environments. Slide 4. Open versus closed systems. This slide focuses on the differences between open and closed systems, a key concept in system theory that applies widely across engineering and technology. 1. Definition. An open system interacts with its external environment by exchanging information, energy, or matter. In contrast, a closed system does not interact with the outside world and remains self-contained. For instance, an autonomous vehicle is an open system because it continuously processes data from roads and surroundings. Meanwhile, a mechanical clock is a closed system since it operates independently once wound. 2. Input-output. Open systems rely on external inputs and outputs, while closed systems operate without external influences. For example, a weather model takes real-time atmospheric data as input, open, while secure data storage is a controlled, closed system with no external communication. 3. Adaptability. Open systems are flexible, they adjust to changes in the external environment. Closed systems, on the other hand, are fixed and do not adapt dynamically. This adaptability is crucial in fields like robotics, where machines must respond to new inputs. 4. Complexity. Open systems are more complex due to their interaction with multiple variables. Closed systems are generally simpler as their behavior is predictable and contained. 5. Feedback. Open systems receive and process feedback, allowing them to adjust performance. Closed systems have little or no feedback, leading to consistent but inflexible outcomes. For example, a communication network, open, adjusts signals based on feedback, while a sealed circuit, closed, runs without external influence. 6. Stability. Open systems are less predictable because they change with external inputs. Closed systems are stable as they are insulated from external changes. 7. Applications. Open systems are common in dynamic environments, like ecosystems or AI-based systems, which need continuous adaptation. Closed systems are used in controlled settings, like data encryption or mechanical devices, where consistency is required. Understanding the distinction between open and closed systems helps in engineering designs, ensuring adaptability in open systems and security or consistency in closed systems. Slide 5. Advantages and disadvantages of open systems. Advantages of open systems: flexibility. Open systems easily adapt to external changes. Scalability. They can expand to handle more data or users. Feedback integration. Open systems use input to improve performance. Innovation. They allow continuous improvement through external interaction. Real-time adjustment. They can respond immediately to new inputs. Information sharing. Open systems exchange data across networks. Environmental awareness. They monitor and react to external conditions. Disadvantages of open systems. Security risks. Open systems are vulnerable to external threats. Complexity. They require complex designs to manage external inputs. Unpredictability. Their behavior may be influenced by outside factors. Resource intensity. Open systems often consume more resources. Maintenance challenges. Continuous input means frequent updates. Data overload. Excessive input can lead to information clutter. Dependency. They rely on external factors to function properly. Slide 6. Advantages and disadvantages of closed systems. Advantages of closed systems. Security. Closed systems are protected from external interference. Stability. They offer consistent performance over time. Simplicity. Easier to design due to limited variables. Efficiency. Operate with minimal resource use. Consistency. Deliver reliable outputs without external influence. Isolation. Immune to environmental disruptions. Reduced error. Fewer variables mean lower risk of malfunction. Disadvantages of closed systems: limited adaptability. Cannot adjust to changing conditions. Fixed functionality. Restricted to predefined tasks. Lack of feedback, cannot improve from external input. And flexibility, difficult to modify after implementation. Outdated systems, risk becoming obsolete over time. Isolation, no communication with external systems. Scalability issues, hard to expand without redesign. In summary, open systems are dynamic and adaptive, while closed systems offer stability and security, each serving unique engineering needs.